Alright, so in this video, what we're going to do is we're going to look at a couple of different ways of expressing how electrons get kind of pumped into an atom in terms of how we express where those electrons wind up. One of the probably most straightforward ways is through an atomic orbital diagram. Okay, and basically what an atomic orbital diagram is basically just a graphical representation of the relative energies of the orbitals that might be involved in a particular atom. So let's say we're looking at lithium. Lithium has 3 protons, and therefore a neutral lithium atom is going to have electrons in the 1s orbital and in the 2s orbital. The 2s orbital being higher in energy, so we literally draw that above the 1s orbital. Then we symbolize the presence of electrons by using half-headed arrows. Now, remember, in order for us to have 2 electrons in a single orbital, those 2 electrons have to have opposite spin. So you can see here I've paired these 2 electrons up, but because they have opposite spin, they abide by the rule that no 2 electrons can have the same set of quantum numbers. Then the 3rd electron is going to go up here in the 2s orbital. Okay, again, that's just one way for us to do this. Another way is by drawing out electron configurations. Okay, so when we're looking at electronic configurations, what we're doing is we're just symbolizing the presence of the electrons by writing down the name of the orbital that they occupy and the number of electrons that are present. So for example, if we're looking at hydrogen, hydrogen is going to have 1 electron, and the lowest energy orbital that it can go into is the 1s orbital, so we put 1s1, showing that there's 1 electron in the 1s orbital. Now helium, I want to draw this clear on the other side so it kind of matches its spot on the periodic table, has 2 electrons, and both of those fit in the 1s orbital as well. But notice what we've done here in this first row of the periodic table. We have filled up the outermost shell. We say that helium has a filled valence shell, and that word's going to have a lot more meaning as we move along here. Let me fix that real quick. Okay, so now we can't put any more electrons in the first energy level. So then we move our way down to the second energy level, which brings us to lithium, okay, which we've already seen before. Now, there's 2 different ways that we could express lithium's electronic configuration. Either we can show it as 1s2, okay, so filling up that first energy level, followed by a 2s1, or we can recognize that lithium is actually building on the full shell of a helium atom. Oops, not a 2s2, but a 2s1. And then beryllium is going to be the helium atom plus 2 electrons in a 2s orbital. Okay, now we're going to jump over a little bit. We're not going to pay too much attention to the transition metals just yet, but we will come back to them. That's why I'm not leaving a big space there. So boron is going to be a helium atom, 2s2, p1. Then we get to carbon, which is a helium core, 2s2, 2p2. Okay, and we get to nitrogen, and this is where things start looking a little bit weird, and that's because the p orbital can hold more than 2 electrons, so this is going to be 2s2, 2p3. Then we'll have oxygen, fluorine, and then we hit neon. Okay, when we get to neon, it's going to be a helium core, 2s2, 2p6. Okay, so again, we can see here that by the time we get to the end of end of the row on the periodic table, we have filled the valence shell again. Now the next element down is going to be sodium, and that's going to build off of a neon core, and that'll be 3s1. Okay, now I'm not going to go through the entire periodic table like this, but I just wanted to point out the way that the periodic table is laid out is that as you go from left to right on the periodic table, you are filling up the valence shell. Every time you go down a row on the periodic table, or down a period, what you're doing is jumping up to the next energy level. Okay? And we'll talk about the effects that that's going to have on the way things behave when we get into chapter 8. Okay, so now, as I mentioned earlier, we need to start talking about the transition metals. In the transition metals, we start seeing some anomalies. Okay, there are some elements that are not going to perfectly follow the rules for electronic configuration. In other words, they're not going to fill up the orbitals in the order that we might have expected. And due to our abbreviated semester here, we're not going to be able to get into that too deeply, except to say that there are some elements where you're going to throw electrons into the s orbital instead of the d orbital, where you didn't expect them to. Okay, one thing we can talk about though is the electronic configuration of metal cations. Okay, now when we're talking about metal cations, we're talking about things that are positively charged and therefore have fewer electrons than the neutral version would have. So for example, we know that lithium as a neutral atom has the electron configuration 1s2, 2s1, whereas lithium plus, the cation, which is the most common cation of lithium, is going to be just 1s2. They'll have one fewer electron, and that electron comes from the highest energy electron that's present. Where things start getting a little dicey is when we're looking at the transition metals. Okay, so for example, with iron, iron has an electron configuration of an argon core plus 2 electrons in the 4s orbital and 6 electrons in the 3d orbital. Okay, but if we're talking about Fe2 plus or Fe3 plus, okay, the electrons are going to be taken out of the highest energy orbital, but you're going to see the other ones kind of rearrange a little bit. Okay, in both cases here we'll have an argon core. Okay, but it turns out that the electrons that come out are not going to come from the 3d orbital, but rather the 4s. So the electronic configuration is going to be an argon core 3d6 for Fe2 plus. For Fe3 plus, it's going to be an argon core, and since we've already taken away all the s electrons, it comes out of the d orbital, so it's 3d5. And that's going to hold true for just about all the cations that we're going to look at. Okay. Now there are 3 key rules that we need to remember here when we're talking about electronic configurations and just generally placing electrons all together. The first was the Aufbau principle. Okay, and that tells us that electrons prefer lower energy orbitals, which makes sense. Okay, and then we haven't talked about this yet, but we have what's called the Pauli exclusion principle. Okay, and although we haven't used that name explicitly, we have described what it implies, and that is that you can't have 2 electrons with the same set of quantum numbers. Okay, and we saw this manifest itself when we were looking at the atomic orbital energies, and we saw that the electrons that were occupying the same orbital had to have opposite spins. There's a third rule here called Hund's rule, and Hund's rule only comes into play when we're talking about orbitals that have more than one suborbital. And before I actually put a definition to this, I just want to give you an example of what I'm talking about. If you consider nitrogen, okay, nitrogen is going to have 7 protons, therefore 7 electrons. Okay, one way that we can distribute those electrons is like this, where we put the first 2 electrons in the 1s orbital, the second 2 in the 2s orbital, and then the following 3 could be spread out over all 3 of the 2p orbitals. Okay, alternatively, we could have arranged things a little differently. Okay, so instead of having them all spaced out evenly, we could have paired up 2 of them and left one by itself. Okay, we can say that the electron configuration has a greater net spin. In other words, if we treat the spins as if they're additive, we have all 3 pointing in the same direction. That's the greater net spin. However, if we have 2 electrons that are opposing one another, that's going to cancel the spin between those 2. So this is going to have less net spin. Okay, so what Hund's rule tells us is that we need to arrange electrons to maximize spin. Okay, so when we're drawing out an electron orbital diagram, we need to make sure that we try to unpair, or we should try to place the electrons as unpaired as possible. Okay, so this on the left-hand side would be the preferred electron configuration, and it actually aligns pretty well with the reactivity of nitrogen. Okay, which brings us to one final point here, and that is the idea of magnetism in terms of paramagnetism or diamagnetism. So let's consider for a second iron. Okay, we've already talked about iron. We know that it has an electron configuration of an argon core, okay, 3d6, actually 4s2, 3d6. Okay, if we draw out the orbital diagram, I'm going to ignore all the electrons that are in argon there. We see that we have these 8 electrons that have to be distributed across the 4s and 3d orbitals. Okay, so we have our 4s orbital, and we have our 5 3d suborbitals. Okay, you can see here that we have 2 electrons paired up in the s orbital, and then the 6 electrons. If we're going to maximize spin, we need to put 1 electron in each one of these orbitals, and only once we've gotten all of them with 1 electron do we pair one up. Okay, so you can see here that we have a net spin. Okay, whenever you have net spin, we say that that particular atom is paramagnetic. Okay, which means that that atom is going to be attracted to a magnet. Okay, the opposite would be diamagnetic, if we were to consider something like, let's see here, um, beryllium. Okay, beryllium is going to be a helium core, 2s2. Okay, so if we look at its electron configuration, we have the 1s orbital and the 2s orbital. We see here that all the electrons that are involved are paired up. Okay, that makes this diamagnetic. And it turns out that that results in it being slightly, not greatly, but slightly repelled by a magnet. Okay, so you need to make sure that you're able to look at an atom, um, whether it's a cation or whether it's neutral, and predict whether or not it's paramagnetic or diamagnetic, based on the way the electrons get distributed. Okay, and that should wrap up quantum mechanics for now.